Hi, so I'm gonna cover the explanation for the midterm solution. So the first question is prove that maximum of the two norm of AU is equal to the first signal value of the single matrix A, and we also have the condition that the two norm of AU is equal to one. So to do this, let's initially use the singular value decomposition of A, where we know that A can be written as USV transpose, and we also know that like these U and V have the properties that UU transpose and U transpose U, as well as VV transpose and V transpose V. All of them are equal to I, the identity matrix. Now we know that S is of this form like sigma 1, sigma 2, etc. to sigma R, where R is the rank of matrix A, and rest all values of that matrix, like the diagonal values of that matrix, is equal to zero, and it's a diagonal matrix, so every other element is also equal to zero. Now, let's decompose the two norm of AU. It can be written as root of AU transpose AU, and then I'm substituting A with USV transpose, and then when you take USV transpose U transpose of transpose multiplied by this thing. There's a transpose missing here, so it should be a transpose. And then when you take that, you have U transpose come to this end, and then you get U transpose V, S transpose U transpose U, S U V transpose U. Now we know that capital U transpose U is equal to I, and then S transpose is equal to S because it's a diagonal matrix. S transpose is equal to S. Now, expanding it, we get U is the vector, small u transpose V S square V transpose U. Now, we're going to do variable, like doing a change of variable. So we're considering V transpose U. U is a vector, V is a matrix. V transpose U as a new vector, which is called Y. So Y is equal to V transpose U. Then to just find the two norm of Y, we can do that Y transpose Y, root of Y transpose Y. So when we do that, we see that it becomes V transpose U whole transpose, V transpose U. And then when you take a transpose, it becomes the order changes and there's a transpose taken to individual thing. So it becomes U transpose, vector U transpose, V transpose U. We know that V transpose is equal to I. So we get root of U transpose U, where U is a vector. Now we know that this is two norm of U. And from the question, we know that U two norm of U is equal to 1, which implies that two norm of Y is equal to 1. And we also have a square. A square can be written like this because it's a diagonal matrix. We can simply square all the diagonal entries of that matrix to get the square of that whole matrix. Now let's get back to our two norm of AU. So two norm of AU is basically Y transpose S square Y, because we had U transpose V, which is basically Y transpose because we took Y as V transpose U. So here we have two norm of AU is equal to Y transpose S square Y. Now Y can be written as a column vector where like it is Y1, Y2, etc. to Ym. And we also know that like this final element Ym, the index M, is greater than R because we know that like Y is the vector which is getting multiplied by A, like say U, sorry, where is it? Here. So U is getting multiplied by A, so it should be like um, the index, the dimension of dimension of U should be like greater than rank of R. The same way, dimension of Y should be greater than the rank of A, because rank is always less than the number of columns or number of rows. It can be like is greater than or equal to. So we are considering that rank is less than this, or otherwise it will go all the way till the last column. So here we know that Y transpose S square Y will become sigma 1 square Y1 square plus sigma 2 square Y2 square, etc. up till sigma r square y r square, and rest all values, since like after sigma r the values of the diagonal entries are equal to 0, so they all go to 0. Now we are asked to find the maximum of 2 norm of AU when no, 2 norm of U is equal to 1. Now let's use substitute whatever we have here in the 2 norm of AU. We get max of 2 norm of y to y equal to 1, because we know that 2 norm of u equal to 1 implies 2 norm of y equal to 1. So this expression, and we know that this expression maxes when we have the whole y concentrated on the y1, because sigma 1, we know that sigma 1 is the greatest singular value of that matrix. So we can say that the whole thing can be maximum when y1 is equal to 1 and all other y's are equal to 0, because the norm has to be equal to 1 after all. So we get that like max of root of sigma 1 square, which is sigma 1. So we finally get that the whole expression that we were looking at, that is like max of AU 2 norm when 2 norm of u equal to 1 is equal to sigma 1. So that's it. So it was very simple. Now let's go into the second question, where we have a function that is given like this two entries, f1 and f2. So f1 is minus x1 plus x2 x1 x2, and the f2 is x2 minus x1 x2. Now we are asked to find if the function is Lipschitz continuous, and the Lipschitz continuous constant. So the Lipschitz constant. So we know that Lipschitz continuity in X happens when we can find an expression in this form. Let's say the f of x minus f of y is constrained by a function multiplied by norm of x minus y. Now we are trying to find that function. I already have the results, but like that's what we are trying to find. Now to find that, we know that to find that particular constant, the way to go about is to find the Jacobian and take the norm of the Jacobian and use the mean value theorem to create a bound for that f of x minus f of y, norm of f of x minus f of y. Now, since the function is this one, the Jacobian can be found by like df1 by dx1 and df2 by dx1 and df1 by dx2, df2 by dx2. Now, if we do differential of this function, that is f1, df1 by x1, we know that minus x1, like minus this first part, if you take a differential with respect to x1, we get minus 1 plus x2. In the same way, if you take this expression with respect to x2, you get this one goes to 0, and this one you will get x1. So that's why we have x1 here. Now, similarly, if you do this one, we see that if you differentiate this f2 with respect to x1, then this is 0. This one will become minus x2. So you have minus x2 here. And then when you differentiate this one with respect to x2, you know that this is x2 by like differentiated with x2, it's 1 minus x1. So 1 minus x1. Now, next thing is to take the norm of this one. So it's a little tricky. Like we also have like we are only asked to find the local Lipschitz constant. And what do you mean by local? When the norm of x is less than or equal to r. So we know that the norm of x is less than or equal to r. R can be a scalar. R is a scalar. So now this implies that we have a two indexed x, which is basically two-dimensional x. So there is x1 and x2. So now the maximum value of x1 or x2 can only be r. You can imagine it like a circle. So for a circle, if it's basically present inside a circle in xy plane, and x1 can go max till r, and x2 can also go max till r. Anywhere in between, the whole norm of x will be less than r. So now we need to find the induced norm of this one. Why induced norm? Because it's a matrix. We can't find the direct norm. So we take the induced norm. Now what we have considered here is induced norm can be maximum individual norms of sum of individual norms of all these individual elements in the matrix. So this is a way to like find a bound for this particular matrix. And when we take the induced norm of this particular Jacobian, we get that it is bounded by the sum of all norms of these values. So if we take this norm, we know that x2 is bounded by like r. So 1 minus x2 can maximum be equal to r plus 1. R is like the bound that we kept for like x, the norm of x. Similarly, x1 can be maximum r, x2 can be maximum r. This one, 1 minus x1, can be maximum 1 plus r. So, so we finally we get the df, the norm of induced norm of df can be maximum to 4 times r plus 2. That's like a scale. 4 times r plus 2 is a scalar because r is a scalar. Now, by mean value theorem, we can write that norm of f of x minus f of y is less than or equal to norm of the Jacobian, induced norm of the Jacobian multiplied by x minus y. Now we also know that this norm is bounded by this particular value. So we can replace that value with this one because there's no change of the equality operator, because this will be like always greater, like less than this value. So we can, without change of this inequality, we can write this expression like f of x minus f of y is less than or equal to 4r plus 2 multiplied by norm of x minus y. Now, when you have this equation, this is basically the function equation for Lipschitz continuity. And by Lipschitz continuity, we know that if we have this expression, then the function is Lipschitz continuous. And this thing that this constant function or constant value over here is the Lipschitz constant. So Lipschitz constant is given by 4r plus 2. That's what we are asked to find this in this question. So let's move forward. So we are given another differential equation which is given by like x dot equal to a t. So a is a time varying matrix. Time varying a has time varying functions inside the each element inside the matrix A. So x dot equal to a atx plus bt ut, and x of t not equal to x dot. Now we asked to find, so we asked to prove that the vector differential equation has a unique solution. So by like from the lectures we know that if the vector differential equation like has all the so if we write the vector differential equation as x dot equal to f of x comma t, that's a function of x comma x and t. It can be anything. So this particular thing that you have here can be written as a f of x comma t. Now, this function, this vector differential equation will have a unique solution if we have this f of x comma t is piecewise continuous in t, and it is also Lipschitz continuous in x for all t. That is element of like r plus. Now we know that this is a function. Now, how do we know that it's a piecewise continuous in t? Because we know that a of t is piecewise continuous, p of t is piecewise continuous, and u of t is piecewise continuous. So any function of a and b will also be piecewise continuous. So here the expression that we have is a function of a, b, and u, which all are piecewise continuous. So the function, the whole equation is also piecewise continuous in t. Now let's look at how we can prove that f of x comma t is Lipschitz continuous in x. To do that, we take norm of like x of t minus f of y of t, y comma t. So if you take that, like replace x with y on the second expression, so you get p of t and b of tu on one side and p of t on the other side. It gets cancelled because there's a negative sign in between. So you only have a of tx minus a of ty, which can be like written as a of t multiplied by x minus y, because it's a vector equation. Now, this one can be bounded by the induced norm of a of t. So that's basically the induced norm property, where you can say that this expression can have maximum value of induced norm of a of t multiplied by x minus y. So with that, you can say that f of x comma t minus f of y comma t yt is the less than or equal to induced norm of a of t multiplied by x minus 1. Now, what we have here is the Lipschitz continuous continuity expression. So this means that this function is Lipschitz continuous. And do we have any constraints on t? No, we don't have any constraints on t. We don't have any constraints on x, which means it's globally Lipschitz continuous in x. Therefore, f of x is the one that we have, the vector differential equation. is piecewise continuous in T as well as Lipschitz continuous in X for every T implies there exists a solution and the solution is unique. Okay, that was a little tricky, but let's go into the third one. So here we are given a differential equation x dot equal to ax plus ut. We can observe that a is not a function of t, so it's a linear time invariant matrix. And this function, when ut equal to zero. So the first question is ut equal to zero. When ut is equal to zero, x dot is just equal to ax, which is a linearly time invariant differential equation. So for a linear time invariant system, they are asking us to find x of t as a function of as a alpha t multiplied by v, where v is the eigenvector of a, and alpha t has to be a scalar function of time. Now, to find that, we know that for a linear time invariant system, we can we can write the solution of the differential equation as x of t equal to e raised to at x naught, where a is linear time invariant, time invariant. Now we have x of t equal to e raised to at v. Now v is a eigenvector, so we know that av is equal to lambda v. That's eigenvector equation, eigenvalue equation, where lambda is the eigenvalue corresponding to that eigenvector we have. Now, e raised to at can be expanded as I plus at plus a square t square divided by 2 factorial plus a cube t cube by t factorial plus etc. It's an infinite series expansion of e raised to at. Now, when we multiply it by v on the right side, we get I dot v plus atv and a square t square by 2 factorial v. Now, let's look at each and every terms of this equation. Now, we have I dot v. I dot v is basically identity matrix multiplied by v, which is equal to v. You get it. Now, next one is ATV. Now, T is a scalar, so you can take V inside. So we can have AVT. And similarly, A square V by 2 factorial multiplied by T square plus etc. All the terms, the same thing can be expanded. Now, since we know that AV equal to lambda V, we can write this first one as lambda VT. And the second one, A square V T square by 2 factorial, you can write it as A multiplied by AV, where AV can be replaced as lambda V. So A lambda V. Then again, you can take lambda outside because lambda is a scalar. You will have lambda AV, where AV is again again equal to lambda V. So you get lambda V, which is lambda square into V. Now, similarly, you take any expression, expression like A cube V will get lambda cube V. So that's like a transformation. Like we can using the eigenvector equation, we can transform it that way. Now, x of t is equal to e raised to at v, and this can be expanded as by using this changes, we will get v plus lambda square v by 2 factorial, lambda cube v by 3 factorial plus extra. Now, v can be taken outside on the right side. We get 1 plus lambda square t by 2 factorial plus etc. Now, this thing over here is the is basically the infinite series expansion of e raised to lambda t. Now we get x of t equal to e raised to lambda tv. Now we have this in the form that we are asked for, and where alpha t is equal to e raised to lambda t. And alpha t is a scalar function of t. That's what the constraint was. And we have satisfied it, and we have the solution here. Now, e raised to lambda t is like 1 plus lambda t. So you can see that this is a function of scalar function of t. There's no matrix involved in here. So it's a scalar function of t. Now, so that's pretty simple. It was tricky to solve it in the midterm, but yeah, it looks simple once you understand the situation, like understand the each properties very well. Now let's go to the next one. We are asked to find the solution of the dynamic system, where u of t is equal to e raised to t v. Now, when u of t is equal to e raised to t v, we know that the function becomes x dot equal to ax plus e raised to tv. Now, for that function, we know that we can find the solution by using this equation. X of t is equal to phi t naught x naught plus integral t naught to t phi t tau b u tau d tau. B is basically 1 here because like we have 1 times ut. But just to have the equations correct, we can use bu tau. And it's basically u tau. Now, what is t naught here is zero because it's given in the equation. So if you remember the question over here, we know that x of zero equal to v. So the t naught here is basically zero. So we know that t naught equal to zero, x naught equal to v, and phi t tau is equal to e raised to lambda t minus tau, and b is equal to 1, u of t equal to e tau v. It's given in the from the question. Okay, so let's find x of t. X of t equal to e raised to lambda t v. That's basically substituting all these things, you will get this particular function. Okay, e raised to lambda t v plus integral 0 to t e raised to lambda t minus tau e raised to tau v d tau. Now, now what I'm gonna do here is taking this tau inside here because it's e raised to something multiplied by e raised to something, so it becomes e raised to this plus this. So it becomes lambda t plus tau minus lambda t because I have took this expanded this one. So you get lambda t minus lambda tau. So lambda tau goes on the other side. Now we can observe that lambda t e raised to lambda t is common on the left hand side and v is common on the right hand side, and they are like not dependent on tau. So you can take it outside of this integral and you get e raised to lambda tv plus e raised to lambda t integral of 0 to t e raised to 1 minus lambda t lambda tau d tau multiplied by v on the right hand side. Now I'm taking the integral, so we know that e raised to kt dt is basically e raised to kt by k, like with the limit zero, like the zero to t. Now we have a catch here. So this integral is only valid if lambda is not equal to one, because if lambda is equal to one, this goes to infinity and it's invalid. So this solution only exists if lambda is not equal to zero. We will consider the lambda equal to one condition later on. So if we have lambda not equal to zero, then we can write it as this way. And when we substitute the upper limit and lower limit, we get that the final solution is basically e raised to lambda t into 1 plus e raised to 1 minus lambda t minus 1 by 1 minus lambda. When you take when you multiply like 1 minus lambda on the 1 and then add these together, you get e raised to 1 minus lambda t minus lambda divided by 1 minus lambda. Now you can multiply this e raised to lambda t inside. You can see that there's a minus lambda multiplied by t here, so that's get cancelled. And final equation, you will get e raised to t minus lambda multiplied by e raised to lambda t. So the lambda is this one and e raised to lambda t is this one. So divided by 1 minus lambda and multiplied by v. Okay. So this is only valid when lambda is not equal to 1. So what happens when lambda is equal to 1? When lambda is equal to 1, so let's go back to this equation here. When lambda is equal to 1, this will become e raised to t v plus e raised to t integral of 0 to t. And when lambda is equal to 1, this is 0. E raised to 0 is 1. E raised to, so this integral, whole integral becomes 0 to t 1 d tau v. So that's what we have here. So e raised to t v plus e raised to t integral 0 to t 1 d tau v. Now, when you integrate 1 d tau, it is t. So t minus 0 divided by 1, which is like t. So you get e raised to t v plus t e raised to t v. E raised to t can be taken outside. So you get e raised to t into 1 plus t v. So that's the solution when lambda is equal to 1. So you have two different like functions, but basically that's like dependent on the lambda. So depending on the what lambdas you have for the matrix, you will have different solutions for x of t. Whatever the solution be, you can see that it is a okay. So there is a small mistake that I've done. So this v has to be here as well. So if you you have to have this v here also. So that's something that I missed when I copied the solution. So this v has to be here. So you see that both the solution has v in the end, which is basically saying that the solution that you have is a scalar function of t multiplied by v. So that's basically what we were asked to find, and we have found. The fourth one was to draw the portrait of Rudolf Lipschitz. This is something that I found in Wikipedia, and great guy. And I'm not a portrait, so I can't draw portraits, so I'm just putting the picture here. Thank you for listening.